Hello from the world of industrial automation. My name is Artem Melnik, and I am a software engineer with 15 years of experience in developing firmware and software for programmable logic controllers, as well as integrating CODESYS runtime into these firmwares. Let's develop an automated control system for an industrial dry heat sterilizer, which is used to disinfect metal instruments, for example, in the medical or beauty industries. Web visualization allows you to control the automated system using any device with a browser, including your smartphone. All the mentioned devices are connected to each other through a router that has internet access. Let's go over the emulator algorithm. With this signal, we can encode the temperature for our range from 0 to 200 degrees with an accuracy of 0.2 degrees Celsius. But this level of accuracy for our range can actually be improved. Let me know in the comments if you know how to do this, or maybe you want me to show this method in future videos. Write in the comments what other settings you would add to the emulator project. After all, it's obvious that a sterilizer has characteristics like heater power, tank volume, and thermal insulation, and depending on the sterilizer model, all of these characteristics I mentioned can be completely different. Let's take a look at the old temperature change graph inside the sterilizer chamber. As you can see from the graph, the cloud service draws straight lines during all phases of the sterilizer's operation: heating, holding temperature, and cooling. In other words, in all phases, we see an absolutely linear relationship between temperature and time, since our emulator algorithm increases and decreases the temperature at a constant rate. Let's fix this behavior in the emulator project and create a realistic physical model of the thermal balance, or simply put, a realistic physical model of the temperature change process inside the sterilizer chamber. For this purpose, I have improved our emulator a bit. Let's switch to the web visualization of the updated CODESYS project and take a closer look at its new features. The first parameter is the thickness of the sterilizer's metal walls, which we can adjust from 1 to 4 millimeters. The second parameter is the thickness of the sterilizer's insulation, which we can adjust from 40 to 200 millimeters. The third parameter is the type of insulation material. We can choose, for example, rock wool, which is a type of mineral wool, basalt wool, fiberglass, polyurethane foam, or ceramic fiber. For each type, we can set the thermal conductivity coefficient of the insulation material. The higher this coefficient, the faster the sterilizer chamber loses heat. Let's see how these parameters affect the process. The thicker the metal walls and insulation, and the lower the thermal conductivity coefficient of the insulation material, the better the sterilizer chamber retains heat, and as a result, consumes less electricity compared to a second sterilizer with thinner metal walls and insulation, and a higher thermal conductivity coefficient. But this model also has its advantages: a lower price and lighter weight of the sterilizer. The fourth parameter of the emulator is the volume of the sterilizer chamber, which we can set from 10 to 500 liters. The fifth parameter is the mass of the metal instruments to be sterilized, which the end user loads into the chamber for disinfection. Let's see how these parameters affect the process. The larger the chamber volume, the more instruments you can sterilize in one load, but the longer it takes to heat the chamber to the target temperature. As a result, you get higher energy consumption and cost compared to a sterilizer chamber with a smaller volume. The sixth parameter is the sensor type. We can choose different types of sensors, and for each type, we can also set the inertia or time constant of the internal temperature sensor. The higher this parameter, the slower the sensor responds to changes in the actual temperature inside the sterilizer chamber. The seventh parameter is the heater power control mode. We can select 2-position mode, 100-position mode, or manual mode. For manual mode, we can set the maximum number of positions for controlling the heater power. If you set 1 for manual mode, this will correspond to 2-position heater control, where 0 means 0 power, the heater is off, and 1 means maximum heater power. The heater is on. The 8th parameter is the heater type. We can select different types of heating elements, and for each type, we can also set the heater's power. The higher this parameter, the faster the sterilizer chamber heats up. The 9th parameter is the external room temperature, which is necessary for implementing a realistic physical model of the thermal balance. The 10th parameter is the initial actual temperature inside the sterilizer chamber, which is also necessary for implementing the physical model of the thermal balance. All the settings I mentioned are saved in non-volatile memory, that is, in the so-called retain area of the SPC210 programmable controller. This means that all the setting values will be preserved even after the controller is powered off. Let's press the power button on the enhanced emulator and also press the power button in our main project and watch the process of temperature change in the emulator. The first value is the current active power of all heating elements. It equals the current maximum power of the heater, since the emulator uses a 2-position power control setting, and for now, supports only one heating element. The second value is the current heating rate, which decreases over time. More precisely, it decreases according to the laws of the physical thermal balance model that we implemented, taking into account the settings we specified. The third value is the current cooling rate, which is 0 during the heating phase. The fourth value is the net power or thermal balance, meaning the current active power minus heat losses. The fifth value is the temperature sensor reading inside the sterilizer chamber. This temperature is read by our main sterilizer project from the analog input of the MV210-101 module. The sixth value is the actual temperature inside the sterilizer chamber. As you can see, the temperature sensor readings lag behind the actual temperature during the heating phase, because when the heater is on, the rate of change of the actual temperature increases. This difference fully corresponds to the inertia or time constant set in the internal temperature sensor settings. Now, for the current 15-liter sterilizer modification and the current emulator settings, based on the chart in the cloud, we can say that our thermal balance model is very close to the actual physical process of temperature change inside the sterilizer chamber. Today, we skipped the surprise section, but in the next video, we will definitely go over the equipment connection diagram and start studying the emulator algorithm. For now, I invite you to point out any shortcomings in the prototypes that you noticed and suggest ways to address them. We also look forward to your suggestions for improving the sterilizer or emulator projects. For example, replacing the temperature control method with a more precise one, such as PID control. Additionally, I'm offering you a choice of the following training video topics, which I've pinned on the channel. How can you use the built-in OPC UA server protocol in CODESYS to integrate SPC210 into popular automation platforms from well-known companies? How can you use the built-in cybersecurity tools in SPC210 to protect against hacker attacks? How can you increase the response speed of SPC210 and the input-output modules polled via Modbus TCP and Modbus RTU protocols in CODESYS? What are the advantages and disadvantages of the Modbus master and slave modes on the Weintek operator panel when used together with the SPC210? What are the advantages and disadvantages of multitasking in CODESYS? How can you use the visualization editor in CODESYS to create a multilingual project and organize screen navigation? How can you use the built-in Linux utility call library in CODESYS to integrate SPC210 with popular automation platforms from well-known companies or with any specialized applications? How can you use the built-in akYtec communication library in CODESYS to bypass the limitations of standard Modbus components? Write in the comments which of these topics interests you more, or suggest your own. Also, if you want to learn CODESYS on real industrial equipment, our channel has the exclusive right to provide a promo code for a 35% discount on purchasing SPC210 and input-output modules from akYtec. To get this promo code, just follow the link below to our WhatsApp or Telegram channel, where you'll find my personal contact listed in the channel profile. You can send me a direct message with the word promo code. Please note though that this promo code is only valid for 24 hours, so only message me if you've already added the products to your cart on the akYtec website. And here's another nice surprise. For those viewers who purchase SPC210 and send me the serial number of their controller in a private message, I will provide all the CODESYS projects used in our channel's videos for free. You can also subscribe to our WhatsApp or Telegram channels so you don't miss announcements about upcoming videos. And of course, so you can always get a promo code for discounts on akYtec products. Don't forget to subscribe to our YouTube channel so you don't miss future videos. And give this video a like if you enjoyed it. That's all for now. See you in the next videos.